Okay, welcome to the second week's online lecture. So in this week, we will study two chapters, as you can see in the slide, chapter 22, electric field, and chapter 23, Gauss law. So the online lecture this time will be slightly longer than what it is usually, so please bear with me. I will try to make it not too long. Okay, before we study chapter 22 and 23, let's make a brief review of what we have learned in the last lecture. In the last lecture, we learned that electric charges interact through the electrostatic force, which we also call the Coulomb force. And we learned that the charges of opposite signs attract each other, while those of the same sign repel. And that the strength of the Coulomb force is proportional to the sizes of two interacting charges and inversely proportional to the square of the distance between them. Okay, do you remember? Okay, good. Now, in this lecture, we will introduce the concept of electric field lines, and electric flux, and learn how to visualize electric field lines. And we will also learn how to calculate electric field around any charge distributions. And then we will also see how to calculate potential energy of an electric dipole inside a uniform electric field. And we will finally learn how to use the Gauss law to calculate the electric field around certain charges. So what is electric field? In order to discuss what electric field is, let's recall the case of two charges interacting with each other by the electrostatic force. We have already studied this in the last lecture. So take a look at the figure on the right-hand side. Here we have two positive charges interacting with each other, and they are repelling, so the arrows are pointing away from each other. We have learned that in order to define the Coulomb force, we needed a pair of charges or two charges, for example, Q1 and Q2. But now, instead of thinking of the Coulomb force as a direct interaction between two charges, let's think about it a little bit a different way. So in this view, we imagine that each charge has a space around itself where it sends off its influence, just like the figure here. And then the Coulomb force may be the result of the other charge feeling the influence from the first charge. If you take this approach, now we can introduce a new concept of the electric field around one charge so that this value can become independent of the size of the second charge. So now let's describe it using mathematics. So in order to do that, let's think about a positive test charge Q0, just like in this figure. So Q0 is located at some distance from the other charged object and is feeling the Coulomb force. But now what we want to do is that we want to divide the Coulomb force by the test charge. So the equation becomes just like this. Now if you divide the Coulomb force, which is F vector, by this test charge Q0, then that's what you get. This is the electric field. This is how we define the electric field. And if you do this, since we have divided by the test charge, now the size of the electric field becomes K multiplied by Q divided by R squared. So please compare this equation with the equation of the Coulomb force. So inside the Coulomb force, there are two charges, Q1 and Q2. But in electric field, we have only one charge. This is the charge around which we want to know the electric field. And now it is pretty obvious, but always remember that electric field is also a vector. So therefore, whenever you deal with electric field, remember it is a vector. And then the SI unit of the electric field is Newton per Coulomb. Why? The SI unit of the force was Newton, and we are dividing it by the charge whose SI unit is Coulomb. So therefore, the SI unit of the electric field becomes naturally Newton per Coulomb. Now let's perform another simulated experiment, this time on electric fields. This simulated experiment is also provided by University of Colorado PHET program. This particular simulation or simulated experiment is designed to give you an idea how electric field looks like, but in fact you cannot really see the electric field. So in this simulated experiment, we will pretend as if we can see the electric field, and here we have one positive charge, and then suppose we have a sensor which can sense electric field, and then let's place this sensor close to the positive charge, and then there is an arrow which represents the electric field. Here you can see that electric field is relatively long, so electric field is strong, and the direction is directly away from the positive charge. So if this sensor is another positive charge, then this arrow will be the direction of the Coulomb force. But now this sensor is not a charge, so therefore you are effectively dividing the Coulomb force by the charge, so therefore this arrow represents the electric field. And let's try to move around this sensor. So if you move this sensor around the charge, then you see that the direction is changing, and then if you get it closer, you see that the arrow becomes longer. Then if you take the sensor away, then you see that this arrow becomes much smaller, which means that electric field is weaker. So therefore the electric field is weaker away from the positive charge, and it gets stronger if you go close. And then this time let's try now a negative charge, and then if you put a sensor, now this time you see that the direction of the arrow is changed, so therefore now arrow is pointing toward the negative charge. So therefore this is how the electric field will look like around one negative charge. And then now suppose you have, say, two negative charges. If you have two negative charges, then you see that now if you take it somewhere in the middle but bottom, then electric field is pointing up, and then when you approach their midpoint, and you see that now you see that now the electric field is decreasing very fast, and then finally disappear, it becomes zero, and then change the direction. Okay, so this is how the electric field look like around this area. You see that if you have two negative charges, then there will be zero electric field right in between them. And then how about two positive charges? In fact, you see that something similar. So it is zero exactly in the middle, but anywhere around, okay, the electric field is pointing away, and then you can see that their length is changing, so you have some idea how it goes. And then now let's try another case. You have one positive charge and one negative charge. In this case, let's see what happens in the middle. Now in this case, if you put the electric field sensor in the middle, and then electric field is actually not becoming zero, but it's actually getting stronger if you approach their midpoint. And then electric field is in fact the strongest around their midpoint. And the reason is simply because now electric field is coming out from the positive charge and is going into the negative charge, so therefore naturally the strength of the electric field will be very strong just between them. Okay. The previous simulated experiment may be useful for giving you an idea about how electric fields may look like, but it is not a good way to represent electric field in a textbook. So in our textbook, it's using a little bit different method, which is called electric field lines. and it is suggested by the Michael Faraday. So let's recall that by definition, the direction of electric field is parallel to the direction of the Coulomb force acting on a positive test charge. So in this figure, now consider the case where we have a sphere filled with negative charges. Then the positive test charge will feel the force upward in this case, but if you move it around, then the force will be always pointing toward the negatively charged sphere. So in that case, we can draw the electric field lines as shown here. So anywhere around the sphere, the electric field is actually going in. And as you can see at the surface of the negatively charged sphere, the force does not actually disappear. It cannot go further just because there is a surface of the sphere, but it does not mean the force becomes zero. So therefore, electric field does not disappear there, but it actually, you can say the electric field line actually touches the surface of the sphere. And so this is the simplistic case. And if you have a positively charged sphere, then electric field lines will look very similar, but arrows, all the arrows will be pointing away. And what happens if you have a bit more complicated case? So if you have a very complex distribution of electric charges, then electric field lines may become a lot more complicated, but there always are common rules that you have to follow. The first rule is that an electric field at any point, a certain point, is tangential to the electric field line that is passing on it. So let's take a look at this picture here. So in this case, the electric field lines are curved. So the vector itself cannot be curved, but here what we mean by this curved line is that if you put the charge at this point, for example here, at this point, it will feel the force which is tangential to this line here. So in this case, we have a negative charge, so the force will be downward, but if you have a positive charge, the force will be upward, but anyway, the direction is following this tangential line. And then along the same line, if you have a test charge somewhere over here, then tangential line will look like this. So depending on the direction of the electric field, if the electric field is drawn using a curve, then the actual direction at each point along curve may be following and may be changing following the shape of the curve. So the rule first is that if you have a curved electric field line, then actual electric field will always be tangential at a certain point. And then the second rule is that the strength of electric field is represented by the density of electric field lines, which means that let's try to compare these two circles, and then these two circles have the same area, but as you can see, inside the left circle, you will see 1, 2, 3, 4 lines. But in contrast, on the right-hand side, you will have only 1, 2 lines. So according to this picture, on the left-hand side, there are more lines per same area, which means that there are a higher density of electric field lines. So in this case, what it means is that electric field strength will be stronger on the area around the left-hand side compared to the area on the right-hand side. Okay. And then the third law is that electric field lines cannot cross each other. It is because at any point, the tangential line to the electric field line will represent the direction of the electric field. But if two lines are crossing, then which line you have to make tangential becomes ambiguous. So remember that electric field lines will never cross each other. Okay, and then now let's try to see, still pretend we can see electric field lines, and then think about how the electric field lines will look like depending on the charge distribution. And then the example shown here is the positively charged sheet. So here what we are assuming is that there is a very large and very thin sheet, and the sheet is filled with uniform density of charges. And then suppose if that charge is positive, and then if you have a test charge which is positive, then naturally this charge will feel the Coulomb force going toward the right side, or the right direction, instead of left. So therefore, here you can see that by following the definition of the electric field, you can see that at this point, electric field direction will be to the right-hand side. And then if this sheet is very large and charge density is uniform, then it doesn't really matter if you shift sideways. So if you go a little bit up, the direction of the electric field vector and probably the size will still be the same. But if you go to the other side of the sheet, then the Coulomb force will be along opposite direction. Therefore, again, the electric field will again be opposite direction. So you can summarize it that on both sides of the electrically charged sheet, the electric field will be pointing away from the sheet if the sheet is positively charged. And of course, if it is negatively charged, then the arrows will be pointing in. And then if the charge density is uniform, then all the electric field lines will be parallel to each other. And in another example, which we actually have seen in the simulated experiment, if we have two positive charges, then each of them will have the electric field lines going out from it. And then in the middle, the left charge will give the electric field going to the right. And then another charge on the right side will give the electric field going to the left. And remember that electric fields are vectors. So if these two electric fields meet at the same position, then what you have to do is the vector summation. So if you add these two vectors, it actually becomes zero. That is exactly the reason why you have seen zero electric field in the previous simulated experiment in the midpoint between the two positive charges or between two negative charges. And then we have also seen in the simulated experiment what happens between one positive and one negative charge. Here what you see is that the positive charge will give electric field going away from it, and then the negative charge, the electric field will go into the negative charge. So naturally in the middle, this is the positive charge's electric field, and probably another vector parallel is the electric field from the negative charge. So by summation, it's still going strong toward the right. And then on the upper side, the positive charge will give off electric field. The direction is a little bit wrong, but you get the idea. It's going to this direction. And then for the negative charge, the electric field is going down like this, and if you make a combination, as a result, the electric field will go this way, and this is more or less tangential to the electric field line at this point. So that's, this exactly follows all the rules that we have discussed in the previous slide. And then actually we are drawing electric field lines only on two-dimensional planes, but in fact we are living in three dimensions. So if you try to draw electric field lines in 3 dimensions, this will look like this.